Hi, welcome to today's session on symmetric key cryptography. So you may remember, because in the last lecture I did an overview of modern cryptography, that symmetric key cryptography is a cryptographic technique where both parties in the communication share the same key. So for example, Alice here is encrypting her note using a key here, and Bob, when he decrypts the note, uses the exact same key. So this is kind of the way that intuitively you would think encryption should work, right? I mean, you have one key that both parties share. Well, there's two types of symmetric key cryptography. The first is called stream ciphers, and the second are called block ciphers. And today we're going to talk about both of those. So let's jump into stream ciphers. So, as obviously being in this lecture, a stream cipher is a type of symmetric key crypto, and it uses a fixed length key to produce a pseudo-random stream of bits. So what that means is you give a stream cipher a key, and it produces an infinitely long stream of bits that should appear random. But the catch is that every time you give that cipher the same key, it should give you the exact same stream. So I pick a key, I feed it into a stream cipher, and I get this infinitely long stream of bits. And then you take that infinitely long stream of bits and you exclusive OR it with your plain text in order to encrypt. And if you want to decrypt, you take that same stream of bits that you get out of the stream cipher and you exclusive OR it with the ciphertext. So in many ways, stream cipher is trying to approximate a one-time pad, which is what you remember as you choose a totally random key that's just as long as your message. In this case, instead of choosing a key that's as long as your message, we're going to choose a much shorter key, and then we're going to use that with the stream cipher to produce this big stream of bits that is as long as the message. So this is not provably secure like a one-time pad, but in practice it seems to do fairly well. Okay, so some real-world stream ciphers. This is the part where I get to say that in practice they may do well, but the most widely used ones have problems. So the first and the most widely used stream cipher is called RC4. Probably the most common way you would be attached to RC4, you would have used it, is it's used in WEP for wireless network security. So WEP is not used as much anymore, but it's still an option on most home routers. It stands for Wired Equivalence Protection. And we're going to talk more about WEP later on in the semester. RC4 is also one option to be used for TLS or HTTPS for encrypting web traffic. But interestingly, it's not recommended that RC4 be used anymore because a lot of people have begun to find vulnerabilities in it. And remember I mentioned that the strength of cryptography is really just based on lots of really smart people looking at it and not finding problems. Well, RC4 stood that test for a long time. Smart people looked at it, didn't find that many problems. But as people have worked on it more and more, mathematicians and others have found problems with it. And so based on that, it's really not recommended that we use it for new things, and so new products don't use RC4, or they shouldn't use RC4. The other really commonly used stream cipher is A5/1. There's also A5/2, the number of increments depending on the revision. But A5/1 is used for encrypting GSM phone data and conversations. So, you have your phone, you make a phone call or you send a text message. Well, that information is sent wirelessly from your phone to the base station. How do you make sure that no one with a random antenna is listening to your phone conversations? Well, you encrypt them first, and A5/1 is the cipher used to encrypt that. Now, a problem with A5/1 is just like RC4, it has flaws in it that have been found. And thanks to the Snowden leaks recently, we actually know that the NSA routinely breaks A5/1 in order to listen in on phone conversations. So there is encryption built into your cell phone for your phone conversations, but it's not that useful because it's broken. People know how to break it. But let's do a stream cipher encryption example. So what's an example of how a stream cipher would work? So we start with our plain text data. This is the thing that we want to encrypt, and a key. In this case, I'm just going to say the key is 128 bits because that's a good size for a normal symmetric cryptographic key, and I want you to get used to those types of numbers. So in this case, we'll have a 128-bit key. We're going to feed that into our stream cipher. In this example, I'll use RC4, and RC4 is going to produce a key stream, which remember is a pseudo-random stream of bits. Pseudo-random meaning it looks random, even though it's not really random. Then we take the key stream and the plain text data, and we exclusive OR it together, and we get ciphertext. Okay, so how would I decrypt in this example? Well, I'd start with that same ciphertext and that same key. I would put the key into RC4. I would get out the key stream. I would exclusive OR the key stream and the ciphertext together. That would get me the plain text. So encryption and decryption actually operate almost identically. You put the key into the stream cipher, you get out the key stream, you exclusive OR that with either the plain text or the ciphertext, depending on what you're doing, and then you get the opposite. But why does that work? What is it about exclusive OR that lets this happen? So there's a few properties of exclusive OR that you need to know, and then based on those properties, I'll build up the mathematical case for why exclusive OR works in this way for encryption and decryption. It's not that complicated, it's just nice to go through it. So here are 3 important properties of exclusive OR. The first is that when something is exclusive ORed with itself, you get 0 every time. The next important property is that when something is exclusive ORed with 0, you get itself. This would normally be like the identity property of a mathematical function. And then down here, this is a really important one. This is the associativity property, which is fairly straightforward. A exclusive ORed with B, and then exclusive ORed with C. It's the same as A exclusive ORed with B, exclusive ORed with C. A lot of mathematical functions that we normally use have this property, but exclusive OR does as well, and that's something I want to point out. Now, so these 3 properties combined together can show us why I can take the plain text and exclusive OR it with the key stream, and then exclusive OR that with the key stream again to get back to the plain text. So anyway, how do I use exclusive OR for encryption? Well, I do the plain text, exclusive OR with the key, and that gets me the ciphertext. When I decrypt, I do the ciphertext exclusive OR with the key, which gets me the plain text. Okay, so those are my 2 basic formulas for encryption and decryption. So why does that work? Well, let's combine them into one longer equation. So I'm going to go ahead and I'm going to take my second equation here, and I'm going to say, okay, ciphertext exclusive OR with key equals plain text. I'm going to substitute ciphertext with this big chunk of information. I'm going to put it right there. So now I have plain text exclusive OR with key, which replaces ciphertext, exclusive OR that with key from here, and get the plain text. Okay, so now I'm going to use the associativity property to just swap the parentheses around. And now I have within this little subset, which is key exclusive ORed with key. Well, something exclusive ORed with itself is always 0. So if that's 0, then I get this equation reduces to the plain text exclusive ORed with 0 equals the plain text. And we know from this second property that anything exclusive ORed with 0 equals itself. So that further reduces to plain text equals plain text, which is exactly what we want to have happen. So mathematically, based on these 3 properties, we can see that the encryption and the decryption do work. And it's because when you exclusive OR something with it, when you exclusive OR something with the key twice, you end up undoing the encryption. So take some time to look at that and think more about it, just to make sure you understand why exclusive OR works in this case. Something like addition wouldn't work in the same way, but exclusive OR does. Okay, so let's do a really simple example, like small numbers of bits. So let's say that I'm encrypting the plain text 01001110 with the key 1100. Okay, so if I go through, this would be 0 exclusive ORed with 1 is 1, 1 exclusive ORed with 1 is 0, 1 exclusive ORed with 0 is 1, 0 exclusive ORed with 0 is 0. So I'll get 1010, just doing a bitwise exclusive OR. Okay, so if I were to take that same ciphertext and decrypt it with the same key, I should get the same plain text, but let's just verify that we do. 1 exclusive ORed with 1 is 0. 0 exclusive ORed with 1 is 1. 1 exclusive ORed with 0 is 1. 0 exclusive ORed with 0 is 0. And that perfectly matches my plain text, just like I would expect. Okay, so that's stream ciphers. You input a key, you get a stream of bits, you do an exclusive OR operation to do encryption and decryption. Another type of symmetric key cipher is a block cipher. Now, a block cipher uses a fixed length key to encrypt a fixed length block of data. So the stream cipher had no limit on how much data you could encrypt. You just generate more key stream and do a bigger exclusive OR operation. But a block cipher encrypts exactly one block of data, and the size of that block is usually fixed based on the algorithm. So as an example, I could have a block cipher that operates on 64-bit blocks of data and uses a 128-bit key. Now this is similar in some ways to a substitution cipher, but just with a much larger alphabet, right? So if we had a 64-bit block cipher, then that would mean that every potential input block has a one-to-one correlation with a potential output block. If that's the case, then our substitution table would have 2 to the 64 entries, which is a lot. That's 1.8 times 10 to the 19 different entries. If I were to try and store that table, I would need 125 million 1 terabyte hard drives. It's huge because we've greatly expanded our search space. So when we did substitution ciphers, when we looked at it in the earlier lecture, we were just talking about 26 letters, right? You take 26 letters and you build a one-to-one mapping. Well, now we're talking about 64-bit numbers and building a one-to-one mapping. And it's just an absolutely enormous table, far beyond anything we could store or compute reasonably. So the goal of a block cipher is to function as a substitution cipher, except to do this, instead of building a substitution table, you simply get the same functionality out of an algorithm and a small key. So what are some real-world block ciphers? One common block cipher is the Data Encryption Standard, DES. It's a 64-bit block size with a 56-bit key size. And I want to note that 56 bits is small. And it was small in 1976 when this encryption algorithm was released. Its size was somewhat negotiated between various government agencies in the US, some of which wanted it stronger and some of which wanted it weaker so that they could potentially break it later. Now, DES was a government standard until 2001. And then in 2001, they standardized on a new cipher, AES, the Advanced Encryption Standard. This is a 128-bit block size, so we have bigger blocks of data we encrypt at a time. And then the key size is variable. You can do 128, 192, or 256 bits for the key size. This is the current government standard, and this is the most widely used block cipher right now. And it's considered very secure. Lots and lots of smart people have looked at it for lots and lots of time and have not found any issues with it. So AES was actually chosen in a competitive bidding process. So a standards agency in the US, NIST, put together a competition where they had cryptographers from around the world design encryption design block ciphers and submit them to this competition. And then after they submitted them, they all spent a lot of time and effort trying to break each other's submission. And then in the end, a small group of finalists was chosen, and AES, in this case, was chosen from that final grouping. So it's a very strong encryption algorithm, and in general, if you need a block cipher, that's the one you should use today, right now. Let's do a really simplified AES example. So encryption, we take our plain text data. In this case, I'm going to say it's 128 bits because we're doing AES, and it uses a 128-bit block size. I'm going to have a key that's 256 bits, just for fun. More keys or the larger the key, the more secure the encryption is. And hopefully we'll have time to do an example of why that is in class. But I feed both of those into AES, and what I get out is ciphertext data of 128 bits. Because remember, a block cipher takes in a block of data and encrypts it with the key to produce a block of data. So 128 bits in, 128 bits out. Now, one thing I'm not mentioning here is exactly what occurs inside of this box. So AES is a complex mathematical algorithm. It uses a lot of different techniques in order to do its encryption, and we're not going to cover those in class, but if you're interested, the entire algorithm is documented in detail on Wikipedia, and it's available from NIST and original research papers and all sorts of things. So that's there, but we're not going to cover that. We're just going to kind of treat it like a black box, but know that it's complex. It's not something simple like, oh, they just exclusive OR the key with the data. No. It's a complex piece of mathematics. Decryption, as you can probably expect, works in a similar way. I pass the ciphertext data and a key into AES, and I get out plain text data. Now, I want to note that AES itself, you tell it whether you're encrypting or decrypting. So in this case, this is AES in encryption mode, and in this case, this is AES in decryption mode. There is a difference with block ciphers. With a stream cipher, there was no difference, right? You just gave it a key and it spit out this big long length of bits. In a block cipher, there's a difference. You're either encrypting or decrypting, and so you have to specify that when you do the operation. Okay, so what are some important properties that block ciphers should have? Well, the plaintext to ciphertext mappings must be one-to-one for a given key. So this means that the same plaintext always becomes the same ciphertext, and vice versa. And this is important because if it wasn't one-to-one, then you couldn't decrypt it. So for example, if you had one plaintext that could become multiple ciphertexts, then going backwards could be troublesome because you would have some other plaintext with no mapping. So they always have to be one-to-one. And also very important is the input and output should have no correlation, which basically means that if I change one bit of an input block, then the change on the output should not be distinguishable from random. What does it mean to not be distinguishable from random? It means that on average 50% of the bits should change. So if I have two different plaintext blocks and I encrypt them, and the only difference between the two is one bit. So as an example here, if I encrypt 11011 as my plaintext, and I encrypt that and I get 00111, and I take another plaintext of 10011, so there's only one bit difference, right? This bit is the different one, the others are all identical. Well, then my output should be seemingly randomly different from this one. There shouldn't be a correlation. So I might see something like that. You can't tell that there's only a one bit difference in the plaintext by analyzing the ciphertext. And this is really, really important. You don't want there to be any correlation between the relationship between ciphertexts and the relationship between plaintexts, because an attacker could use that to figure out something about what was encrypted. So what are important features of block ciphers? Well, there's really only two features, the block size and the key size. And for both of them, in general, the larger it is, the more secure the algorithm is, assuming the algorithm is designed correctly. But that also causes the algorithm to run slower. If you increase the block size, that means that the algorithm is trying to encrypt a larger block of data. It's going to take more time, more mathematical operations. Same thing with the key size. So there's a balance here between performance and security. The bigger key sizes are more secure, but they'll be a little bit slower. Larger block sizes is hard to quantify that way. But in general, bigger would be a little bit more secure, but there's a trade-off there. So now AES seems to have a pretty good balance for the current days. A block size of 128 bits and a variable key size between 128 and 256 bits. 128-bit key size for AES is more than enough for most people, but if you're really, really paranoid, you could use 256. Okay, so summing up. Stream ciphers produce a pseudo-random stream of bits that you exclusive OR with your plaintext. So give a stream cipher a key, produces this big long stream of bits. Block ciphers are used to encrypt data one block at a time, so they can only encrypt a fixed size block. You can't encrypt less data than a block, you can't encrypt more data than a block, you can only encrypt exactly one block. And because both of these are symmetric algorithms, both the sender and receiver need to share the same key in order to encrypt and decrypt and share that information together. Thanks.